Hello, today we're going to be starting chapter 2 and we're going to start with 2.1 functions and their graphs. So we're going to start off by doing some vocab. First vocab word is a relation. A relation is any set of numbers. Basically, a more formal definition is it's a mapping of inputs and outputs. And just think about an equation. You are inputting x values and you are taking out your y values. So inputs are x's and outputs are y. The domain we know is always representing all possible x values. So the domain is representing our input values. And this is also going to be your independent variable. And we know range is representing all possible y values, so that's going to be representing our output. And if that's the independent variable, the range is your dependent variable. Now the tricky vocab word is, what is a function? A function is an equation where every input has exactly one output. And this definition becomes very, very important. So every input, every x value is only going to correspond to one y value. Where it gets tricky is that you can have different inputs, different x values give you the same y. So we're going to go through a couple examples and hopefully it makes a little bit more sense. If you think about a function, you want to think about a vending machine. And you want to think about, is that vending machine functioning properly? And if a vending machine is functioning properly, if you hit, let's say, the Mountain Dew button, you should get a Mountain Dew out of the machine. But it would not be functioning properly if you hit the Pepsi button and got a Mountain Dew. So every single time I hit a 1, I should get a 3 because the button 1 corresponds to 3. Every single time I put in 1 in, a 3 should come out. Every single time I hit a 2, a 6 should come out. Every time I hit a 3, a 6 should come out. Every time I hit a 4, a 9 could come out. And this, again, is very similar to a vending machine. Think about a vending machine. Think about the most popular drink in that vending machine. Sometimes you have 2 buttons that give you the same drink. So is this a relation? Is this relation a function? Yes. We go to our next one. If I hit a -3, I get a 1. If I hit a 1, I get an 8. If I hit a 4, I get a 2. If I hit an 8, I get a 4. Every input is corresponding to only one output. So every time I hit this number, I'm always going to get a 1. So yes, that is a function. And our third one, if I hit -5, sometimes it's giving me a -6, and sometimes it's giving me an 11. Which means this is not functioning properly. If my -5 was, let's say, my Mountain Dew button, sometimes I get Mountain Dew, and sometimes I get, let's say, Cherry Pepsi. So you just want to make sure that everything that you put in, every time you put a -5 in, you're going to get the same thing out. It doesn't matter what you're taking out, but it should be the exact same thing. So if I think about the equation, y equals 2x plus 5, if I put in a value of 1, no matter what I do, I should always get out a value of 7. So my in is 1, my out is 7. If I put a 1 in and I get multiple answers, sometimes I get 7, sometimes I get 6, sometimes I get 20, I haven't been functioning properly. Every input has exactly one corresponding answer. If that input has more than one answer, it's not functioning properly. So that's how we determine if a relationship is a function from a mapping. We also have it from a table. If you're given a table, you can look at it, or you can go ahead and take the table and turn it into a mapping. So I have my x's. My three numbers are 2, 3, and 4 for my x's. Then we have our y's. If I plug in a 2, I get a 4, so the 2 maps to 4. If I get a 3, it maps to a 6. If I get a 3, it also maps to a 7, and a 4 maps to an 8. So this is going to be a no, because when I hit the 3 button, sometimes it gives me 6, sometimes it gives me 7. I don't know what I'm getting. It can only give me one answer. If it gives me more than one answer, it's not functioning properly. We look at our next one. Our x's, our possibilities are 2, 3, 4, 5. Our y's are 4, 6, 10. So 2 is going to map to 4 because 2 corresponds to 4. 3 maps to 6, 4 maps to 6, and 5 maps to 10. Is this a function? Yes. Remember the vending machine. Let's just say that 6 is the most popular soda, which means you have 2 buttons, but every time I hit 3, I'm always going to get a 6. Every time I hit 4, I'm always going to get a 6. So, if you have the same number repeated in the x column, that's bad. If you have the same number repeated in the y column, that's okay. And the last thing that we're going to do, determine if it's a function or not, is from a graph. And if you're looking at a graph and trying to determine whether it is or is not a function, you're going to use the vertical line test. And if you remember the vertical line test, it says if I draw a vertical line, it should only touch in one spot. If I can draw a vertical line anywhere on my graph and it touches more than one time, then it's not a function. No matter where I draw this line, it's never going to touch more than once. So yes, this is a function. If we go to our sideways parabola, if I draw a line right there, it's going to hit 2 times, which means no, it is not a function. Now we want to be careful because I could draw my line so that it goes through the vertex, and if that happens, I'm only touching in one spot. But that doesn't really mean anything because it could be any vertical line. If I can draw any single vertical line on my graph and it touches in more than one spot, that means it is not a function. Even though I can draw one that does work, every vertical line has to work in order for it to be a function. We go to our next graph, which is a cubic graph, or it could be a cubic graph. I draw my vertical line, it only touches once. I do a couple, I'm looking, I'm not really seeing it where it's going to hit more than once, so yes, this is going to be a function. No matter where I draw that vertical line, it's always going to work. Now the next one's a little bit tricky. We have a vertical line. If I draw my line, I haven't crossed it at all. If I draw my vertical line on top of my vertical line, it's touching in all possible infinite number of times. So this one is not a function. And last, we have a horizontal line. No matter where I draw that line, it's only going to touch once. So yes, this is going to be a function. Okay, go ahead and flip your pages over. So now we know how to determine whether or not it is a function. Now we're going to talk about how to write it in function notation. Function notation is not hard. It's not learning a new concept, it's just writing it in a different way. We are used to seeing an equation written as y equals mx plus b, so 2/3 x minus 4. The only difference is if I'm writing it in function notation, I don't have an x and a y. I take out the y and I have f of x. This is telling me that my function is a function of x. So the only change in going from slope-intercept form to function notation is instead of having a y, I'm going to have f of x showing that my x is my input. It is a function of x. And then why not? Let's go ahead and do a quick review on how to graph a line in slope-intercept form. We have our slope of 2/3. We have our y-intercept of a -4. So we start down at -1, 2, 3, 4. Our slope is a positive 2/3, so we're going to go up 1, 2, right, 1, 2, 3. Up 1, 2, right, 1, 2, 3. We also could go down 1, 2, left, 1, 2, 3. So remember, you always start with your y-intercept and then use your slope to build it in both directions. Alright, so that's our simple writing function notation, taking the y out, putting an f of x in its place. Now, how to evaluate in function notation. We have done evaluating so far this year. So we say evaluate this function when x is this, when y is that. We're going to do the same thing. We're going to evaluate, except for instead of being given y's and x's, you're given f of x. And we want to evaluate that when x is equal to 3. So we're going to take that x and we're going to plug it in everywhere that we see it. So 4 times 3 minus 3 all over 3. The benefit of this is telling me what I am inputting. When we plugged something in for y and x, we didn't know what we were plugging in. We would get our y value out, but we would have to look back at our directions to see what was plugged in. So we go ahead and simplify that. 4 times 3 gives us 12 minus 3 all over 3. We simplify our numerator. 12 minus 3 gives us 9 over 3. So our answer is 3. This is representing our output. And again, the benefit to this is now we know a point on our line. Here is our x. Here is our y. So we know a point on our graph would be 3, 3. Now that's not part of the problem, that's not part of evaluating, but that's just something that you should be aware of. What you're putting in is the x value, what you're getting out is the y value. So when I say that f of 3 is equal to 3, I know that a point on my graph is at 3, 3. Okay, our last part of our video is finding domain and range. Remember, domain is all possible x values. Range is all possible y values. So when I look at my function, I have f of x is equal to the square root of x. And remember, f of x is representing the same thing as y. So domain is what can you put in, range is what can you take out. So I think about what numbers can I put in for x. Can I put in 1? Yes, the square root of 1 is 1. Can I put in 2? The square root of 2. It does give me an answer as a decimal, but I can do it. Square root of 3. Yes. Square root of 4. Yes, that's 2. So I'm going to get real answers for everything higher than 1. Ask yourself, does 0 work? Can I plug 0 in? Yeah, the square root of 0 is 0. Can I plug a -1 in? No. If I plug a -1 in, I'm going to get an error message on my calculator. That's going to be a non-real answer. That's going to be our imaginary numbers, which remember we'll talk about later on in the semester. So, in order to get a true answer, I can only plug in positive numbers and 0. So my domain can't include any negatives. So my domain is x has to be greater than or equal to 0. Now I want to think about what numbers can I take out? What numbers would be coming out of that? And again, I can't get any negatives, so my range is going to be y is greater than or equal to 0. What I want you to do is press pause for a second and try to think of, are there any numbers for our second one that we would not be able to put into our equation? Any numbers that we wouldn't be able to take out? So go ahead and press pause. Alright, let's see how you did. We have 1 over x minus 3. So we check numbers. Can I plug in 0? 0 minus 3 gives me a -1/3. I can do that. I plug in a 1. 1 minus 3, I get a negative 2. Negative 1/2 is my answer. I plug in 2. 2 minus 3 is a negative 1. My answer is negative 1. That works. 3 minus 3 gives me 0. Now I have a problem. 1 over 0 is undefined. So anytime you have a fraction, you want to be careful because the bottom cannot equal 0, because then you have an undefined number. The one number that's going to make that denominator 0 is going to be 3. Our domain can be any number except for 3. So our domain is anything but x cannot be 3. So all real numbers except x cannot equal 3. Now I think about, are there any numbers that I can't get? So I have f of x, I have 1 over, and then this number can be anything. I can make that into anything. Some people might have thought, okay, well, it has to be a fraction. But that's not necessarily true either. What if I had 1 over 1/2? We know that dividing is the same thing as multiplying by the reciprocal. So 1 times the reciprocal gives me 2. So even though I have a numerator of 1, if I put a fraction on the bottom, I can end up with whole numbers. The only thing that this fraction cannot be is 0. Because 0 comes from when 0 is on the numerator and you have a number on the bottom. Our numerator has already been predetermined for us. So the one thing that cannot be is 0. So our range is all real numbers except y cannot equal 0. One last thing I want to point out is domain. You want to make sure that you're referring to your x's. For your range, you want to make sure that you're referring to your y's when you're giving me your answer. Alright, and that is it for our video for today.